Good morning, our listeners, and welcome to today's class. Today, we are still continuing to look at the concept of interval estimation. In our previous class already, we had spent enough time giving elaborate introduction on the concept of estimation, which of course was extended to interval estimation, which is what is before us today. Do remember that in our last class, we did say that estimation is categorically classified into two, into what we call point estimation and interval estimation. In the point estimation, the interest is to, from sample observations, obtain a single value called point estimate with which to represent the unknown population parameter, be it theta or be it any other value. However, in interval estimation, rather than now going for a single value with which to represent the unknown population parameter, we now obtain interval of what values that is going to contain or bound the unknown population parameter, be it theta or any other value. In that our previous class already, we had spent time discussing on the construction of confidence interval for the population parameter theta. That is, for instance, that the population parameter theta is given as this. The population parameter is given as what? Theta. Where this theta could be the population mean, where it could be the population proportion, where it could be the population variance, or any other population characteristics. We are now trying to obtain the interval that is going to bound or contain this unknown population parameter theta. We said in our previous class, let this interval be represented with what? L and what? U. Where we now have something like this. L is less than or equal to what? Theta, which is less than or equal to what? U. This L and U are what we are referring to as the interval of the values that are going to contain this unknown population parameter theta. And of course, this our L is what we call the lower confidence limit. And this our U is what we call the upper confidence limit of this confidence interval. Therefore, confidence interval contains two limits: the lower confidence limit and the upper confidence limit. The lower confidence limit bounds the parameter from below, while the upper confidence limit bounds the parameter from what? Above. However, when we talk about constructing confidence interval or constructing interval for unknown population parameter theta, we try to ascribe some level of what? Certainty, or what we call some level of what? Confidence, that this our interval we are constructing is going to include our population parameter theta. And that confidence or that level of assurance brings in what is called a probability in our study. And we are saying that the probability that our L is less than or equal to what? Theta, less than or equal to what? U, is given as what? 1 minus what? Alpha. What we are saying here is that we are 1 minus alpha confident that our confidence interval L and what? U are going to contain the unknown population parameter theta. Or put in another way, that the probability that our confidence interval L and U contains the unknown population parameter theta is given as a 1 minus alpha. And that's the reason why you hear people say construct 1 minus alpha confidence what interval. This 1 minus alpha, of course, is called your confidence level. So what is meant here is that my confidence level, that L and U, which are the interval of values, are going to contain the population parameter theta is 1 minus alpha. This expression is the same thing with this which I want to write. I can equally write this now as P into L less than or equal to what? Theta less than or equal to what? U. Multiply by 100% equals to 100 into 1 minus what? Alpha, or in percent. What did I do here? What I have just done here is to use 100% to multiply the left hand side and use 100% to multiply the right hand side. So this expression and this expression are the same thing because I use the same quantity to multiply both the left and then the right. So what we are saying here is that we are 100 into 1 minus alpha percent confident that our interval or confidence interval L and U are going to contain the unknown population parameter theta. And that is equally why you hear people say construct 100 into 1 minus alpha percent confidence interval. So you either hear them say construct 1 minus alpha confidence interval, or they say construct 100 into 1 minus alpha percent confidence interval. Okay? Now, of course, these are alpha. We now say where these are alpha, where this alpha is what we call level of significance. Level of significance. Which is, of course, what we call the probability of type 1 error, which in this context is going to be defined as the probability that our confidence interval do not contain the unknown population parameter. And of course, that's the reason why this alpha is kept as small as whatever. Something like what we have as 0.05 or something like 0.01 etc. Depending on your level of confidence. Okay? We already had explained all these things that day, but we just want to refresh our mind on it. So in this case now, our interest is what? Our interest is how do we obtain the true value of what? L and U, such that we have the confidence of 100 into 1 minus alpha percent that it is going to contain the unknown population parameter theta. Here, how do we get the true value of what? Of L and what? U, such that we are 1 minus alpha confident that it is going to contain our unknown population parameter theta. That is all what we do in confidence interval. And we already had explained some of all these things now in our previous class. So today we want to go straight into construction of confidence interval for the population mean, mu. So permit me to clear the board. So what we have is construction of confidence interval C dot I. I mean by confidence interval will be C dot I of the population mean, or for the population mean. That population mean is represented with a symbol mu. So don't you see that here now, we are no longer talking about what theta? We are now talking about population mean, and population mean is represented with this symbol mu. Which means in every other illustration I gave earlier now, in the place of what of theta now, I am now going to use what mu. And of course, what now will be before us now becomes something like this, that we are saying our population mean now becomes what we call our mu, no longer theta. And we'll be able to have that our L less than or equal to what mu, less than or equal to what u. And then we'll be able to have probability of L less than or equal to what mu, less than or equal to what u, is given as 1 minus alpha. And then our P of L less than or equal to what mu, less than or equal to what u, multiplied by what 100 what percent, is given as 100 into 1 minus alpha percent. Which means in this scenario now, we are trying to obtain the value of L and u, true value of L and u, which of course will contain this unknown population mean mu. Over here, how do we go about obtaining the true value of L and u, which of course are the confidence what interval that is going to contain this unknown population mean mu with a probability of 1 minus what alpha, or with the confidence level of 1 minus what alpha. So here we are saying that our confidence, we have 1 minus alpha, we are 1 minus alpha confident that our confidence interval L and U are going to contain the unknown population parameter mu. Here we are 100 into 1 minus what alpha percent confident that our interval L and U are going to contain the unknown population mean mu. So that is exactly what we do in this interval, the confidence interval construction. So what we're now going to do now is, the interest now becomes, how are we now going to obtain the true value of this and this that is going to bind this? And on that note, we now take what we call illustrations, or we take what we call samples. So we now have this. Permit me to clean this. We are saying that assuming that we take random observations from the population of interest, and these random observations we have taken are, we have what? X1, comma, X2, comma, up to what? X what? N. And these observations are, of course, what? Independent of each other. Hmm? And then these observations, it has a sample mean X what bar. And this sample mean X bar has a sampling distribution that is approximately normally distributed with mean mu and variance sigma squared all over what? N. I repeat, we are given x1, x2 up to x what? N. And these x1 up to xn are independent observations taken from the population of what? Of interest. And the sample mean is what? X bar. And this sample mean has sampling distributions, or sampling distribution with mean mu and variance sigma squared over n. How are we going to construct confidence interval for this kind of a statement? Number one, when n is what? Is large, and then the population variance is what? Is known. See what I'm saying? How are we going to construct confidence interval here when our n is large and then our population variance is what is known? So I'll give a condition. Number one condition. When our n is large, when n is large and sigma squared is known. Okay? Of course, when we talk about n being large, we are saying our n is greater than or equal to what? 30. That is our observation. Observations in number is greater than or equal to what? 30. And do remember that our interest is that we want to find our L that is less than or equal to what? Mu, less than or equal to what? U, with probability of what? 1 minus alpha. Now, for us to obtain the value of our L and U, where we are 1 minus alpha confident that this our L and U are going to contain this unknown population mean mu, then the value of what L and U should be under this condition when when n is large and this sigma squared is what is known, then we have that my L is equals x what bar minus z of alpha all over what 2 multiplied by what we call sigma all over square root of what n. And then we now have less than or equal to the value of my L has become this. So less than or equal to what I have here is what? Mu. What I have here is what? Less than or equal to. The value of my U will now be U is equals. The only thing that is going to change that instead of here becoming negative, it is going to become positive. So you have x what bar plus z of alpha over 2 multiplied by what? Sigma all over square root of what? N. So this is exactly what you now have. And of course, you know that this your L equals this, and this your U equals it. So you can easily drop out U and drop out L entirely. And what you have becomes that this is equals, you have x bar minus z of alpha over 2 multiplied by what? Sigma all over to what? N. This is less than or equal to what? Mu, which is less than, drop your U, you have x bar plus z of alpha over 2 multiplied by what? Sigma all over square root of what? N. This is this. Therefore, the moment you know the value of your x bar, you know the value of your z of alpha over 2, you know the value of your sigma, and you know the value of your n. The moment you substitute them here now, you'll be able to know the value of your confidence what? Limits that is going to contain this unknown population parameter mu, which is the population mean. This condition is when n is large and this sigma is what is known. We have another condition. That other condition is number two. Number two. We say when n is large, when n is large, but sigma squared is unknown. You see a condition here. We are saying that there is another condition where our n is large, but we were not given this sigma square. It is unknown. When this sigma square is unknown, we go ahead by making use of what we call the sample variance. This is what we call population variance. When n is large, but we are not given this population variance, we now go ahead by making use of what we call the sample variance. And sample variance, of course, is denoted with what? S what? Square. So what you are going to do is to come back to this formula. Anywhere you see sigma, you replace it with S. Just like you had sigma square, but in the formula, what you're having is sigma sigma. Here you have what S square. So what you should be having here is what SS. So in that case, you are now going to have that this formula is now going to be, you have what x what bar minus, you have what z of alpha over what 2, then multiply by. Instead of writing this sigma, you write s all over what square root of what n less than or equal to what mu less than or equal to, here becomes what x bar plus z of alpha over what 2 multiplied by what s all over square root of what n. This is exactly what you are going to have. Of course, this our z of alpha over 2, z of alpha over 2, z of alpha over 2, z of what alpha over 2. They are called, it is called the critical value of the confidence interval. The critical value of the confidence interval. Okay? So this is of course what we do when this condition is this, and this is what we do when condition is this. But what are we now going to do when our n is what small and that sigma square is unknown still? So we have three conditions here. When it is large and this is known, when it is large or this is unknown. Now, what if it is now small and then it is what unknown? What is going to be the value of L and what is going to be the value of what U? Let me show you. That condition is now when, number 3 condition, when N is small and sigma squared is unknown. Okay? And our interest still remains on our P of what? L less than or equal to what? Mu less than or equal to what? U, which is going to be given as 1 minus alpha. Under this condition, what is going to be the value of our L? What is going to be the value of our what? Of our U? Under this condition, the value of our L is going to be, that our L now is now going to be is equals. We have what? X bar, just like what we have here, minus. Instead of having z of alpha over 2, you are going to have t, which is what we call student t distribution. So what you are going to have is what? T of n minus 1 of alpha over 2. Which means multiply by, what you have here is what? S all over to what? N. Here is less than or equal to, here is what? Your mu, less than or equal to. Here is u, and u is this. So you have x bar plus. Instead of writing this z, what you are going to write is what? T of n minus 1 of alpha over 2 multiplied by what? S all over to what? N. You close it. Remember that you can equally drop, just like we did before, yeah, because this is this. You can equally drop this your L and drop this your, okay, I've even dropped to you here. So I can equally come here and drop my L, and then this thing becomes this way. This our n minus 1 is what we call degrees of what? Of freedom. Okay? And the entire of this our t of n minus 1 of alpha over 2. We call it now the value of a student t distribution that locates the area of alpha over 2 at the tails of the distribution. So what I plead with you to remember for me is, what is the value of L and U? In the first condition we gave, in the second condition we gave, and then in the third condition we gave. The moment you can remember all these things now, you don't have a problem. We want to take 1 or 2 questions now under them so that you see how you can solve a problem under them. So permit me to clean here, and then we now take some questions. So I'll clean here. Let me read this question I have to your hearing, and then we write it on the board. Let me read it to your hearing. We have some questions here to solve with you. The first question says, let me tag it now, solve the examples. Tag it, solve the examples. Solve the examples. The first question says, and I write, a manufacturing firm's light bulbs have a length of life that is normally distributed with standard deviation of 45 hours. Standard deviation of 45 hours. So I will now come here under this number 1. The standard deviation, of course, is talking about what? Sigma. And they say that sigma is 45 hours. And know you that if sigma is 45 hours, it means that the variance sigma squared is going to be 45 squared hours. Because, of course, sigma is the square root of the variance. So I read on. If a random sample of 30 bulbs, so my n equals what? 30 bulbs. If a random sample of 30 bulbs has average life of 770 hours, remember that average is mean and mean is x bar. So they are saying that x bar equals 770 hours. Okay? They say find the 95% confidence interval for the population mean of the bulbs. So they asked me to find 95% confidence interval for population mean, which is what? Mu. And there is something they gave me in addition. They came here and said, as a continuation of the question, they say hint that z of 0.025 equals 1.96. When we have this kind of a thing, how do we construct the confidence interval for the population mean mu? Very simple. We ask ourselves question. The question we are going to ask ourselves is, this question given to us, in which category does it fall? Does it fall in the first category where our n is large, greater than or equal to 30, and our sigma squared is what is known? We come here. If you check, our sigma is given as 45, and that was why it was implied that sigma squared is given as this. Therefore, our sigma squared was given. It is known. Then our n is here. N is equals to 30. So n is large. Because n is large now when n is greater than or equal to what? 30. So we can apply what we call central limit theory. So I'm going to solve this problem now using what we call the first condition. And that first condition says, and I write. So as a way of solving it, I now have solution. Solution. Then, of course, my interest here still remains in the P of what? L less than or equal to what? Mu less than or equal to what? U. That will give me 1 minus what? Alpha. Okay? Sure. Now, my interest is now, what is now going to be the value of L? What is now going to be the value of what? Of U? Such that I will have this probability. So what I'm now going to do is, in that first condition, if you remember, we said that our U is going to be, my L now is going to be L is equals. We had what? X what bar minus. We had what? Z of alpha over what? 2 multiplied by what? Sigma all over square root of n. Less than or equal to what? Mu. Less than or equal to, we come here. The only thing that's going to change is this. We have x bar plus, we have z of alpha over 2 multiplied by what we call sigma all over square root of n. Close it. So, in fact, now that you have known, let me be dropping this. So, what I mean here is, of course, you know that from here to here is my L, and from here to here is my what? My U. The lower confidence limit and the upper confidence limit. I want us to look clearly here. If you look clearly here, you find out that when X bar is here, I know it here. Sigma is here, I know it here. N is here, I know it here. The only thing I do not know is my alpha. I don't know what alpha is. But they have told me something that is going to help me know alpha. They asked me to construct 95% confidence interval. 95% confidence interval. Okay? Or what we call 95% confidence level. Whichever way you call it is right. But do you remember earlier that I told us that a confidence level is represented with something like this? That we have, this one is given in percentage. I say confidence level can be given as 1 minus alpha. Or it can be given as 100 into 1 minus what? Alpha in percent. Because they gave me this in percent, I am going to use the one in percent. They told me to construct 95% confidence level. But I know that my confidence level can equally be written as 100 into 1 minus alpha percent. So I'm going to equate this to this. Equating this to this means I will now say, therefore, my 100 into 1 minus alpha percent equals 95%. 95%. Okay? Then at this point in time, this percent and this percent can equally go. And when this percent and this percent goes, what you have become 100 into 1 minus alpha, then is given as what? 9 5. Okay? And then when you have something like this now, what are you now going to have here? What you are now going to have here becomes what is called 100 minus 100 what? Alpha is equals what? 5. That's what you have. So now, this and this are like terms. So what you now have is what? Minus 100 alpha is given as 95 minus what? 100. And then minus 100 alpha is given as what? Minus 5. So that this can cancel this. And making this alpha solve, you have that alpha is equal to 5 all over 100. And this will give me 0.05. So I have now known that alpha is 0.05. How did I know this? From this idea that my confidence level is 95%. And based on what we said earlier, we said that this thing can be given as 100 into 1 minus the alpha percent. Now, because our alpha is 0.05, we now come here. Are you now seeing that here is what? Alpha over 2. So we are now going to say here is now 0.05 all over what? 2. So we want to solve now proper. I have known what my alpha is, 0.05. Then I will now come here. Permit me to clean here. You know what I mean by this? So I will now come here, and what I will now write here now becomes, I will now see that this equals, I'll open the bracket. What is my x bar? 770. So in place of x bar, I'll write 770. What's the sign here? Minus. What is here? My z of 0.05 all over what? 2. That's what is here. Z of 0.05 all over what? 2. Then multiply by. What is sigma? 45. So I have 45 all over. What is my n? 30. So I have square root of what? 30. This is less than or equal to what? Mu. Less than or equal to. The whole thing that is written here will be written here, except that here is going to be positive. So here is 770 plus z of 0.05 all over 2 multiplied by what? 45 all over root what? 30. You close it. And do remember that 0.05 divided by 2 is 0.025. Okay? So in that case, what I now have here becomes that this equals 770 minus z of 0.025 multiplied by what? 40 what? 5 all over to what? 30 is less than or equal to what? Mu, which is less than or equal to 770 plus z of 0.025 times 45 all over root what? 30. And we are given a hint that we should note that the z of 0.025 is 1.96. So what I'm going to do is to quickly come here. Anywhere I see z of 0.05, I'll put 1.96. And this thing becomes finally, that is 770 minus, this is 1.96 times 45 all over root what? 30 is less than or equal to what? Mu less than or equal to what? 770 plus 1.96 times 45 all over to what? 30. Close it. So once you use your calculator and you say 1.96 times 45 divided by root what? 30, minus it from this, you get your lower class limit. Once you now do for yourself the 1.96 multiplied by 45 all over root 30 plus 770, you now get the upper class what? Limit, upper confidence what? Limit. And those values now will now stand for what we call the confidence interval that will be able to bind this our unknown population mean mu. So you can just press your calculators and get their values, because trying to get it here is going to make the size of the class very large. Okay? Thank you very much for your audience thus far. Let us draw up another question from here. So these are what we have done. This is our formula for the first condition. First of all, we read out the question. We wrote our sigma to be this, sigma squared to be this, n to be this, x bar to be this. We are looking for 95% confidence interval, then that will contain this, and they gave us this hint. We first of all check the condition at which this thing fell into. And we notice that the condition that this thing fell into is the first condition, where the population variance is known, and then the n is what is large. And the formula we use in that condition is this. And that was the formula I used here. Thank you very much. So permit me to clean the board. Let us draw up another question, and then we see how it goes too. Another question we want to draw says, and I read, that question says, the mean and the standard deviation for the quality grade point average of a random sample of 49 students are calculated to be 2.2 and 0.3. And remember mean. They say the mean and the standard deviation. And the mean is x bar. And the standard deviation here. They have already, I repeat, the mean and the standard deviation for the quality grade point average of random sample of 49 students are calculated to be 2.2 and 0.3. So in this case, the sample, the population standard deviation is unknown. It was calculated from sample. So I'm not going to write it with sigma, I'm going to write it with what? S. So in this case, what they did in that number 2, they told me They told me in that number 2 that the mean and the standard deviation of the quality grade point of a random sample of 49 students are calculated to be, so x bar calculated to be equals what? 2.2. And then my S is given as what? As a 0.3. Okay? And then they say random sample of 49 students. So it implies that my N is equals to 49. We go ahead. They say find the 90% confidence interval for the population mean. So they want me to find 90% confidence interval for mu. And there is something they said. They went ahead and told me hint that z of 0.005 equals 2.575. So how do we solve this kind of problem? First of all, we now think of which condition does this thing fall into? Is it our first condition? Is it our second condition? If you watch here, what I have here is S, not a sigma. Because they say this standard deviation was already calculated from a sample taken, not that it is known that the population has a standard deviation of this. So it fell under the second condition, where my N is large because N is 49, but my sample standard deviation, the population mean variance is unknown. So I am using the sample standard deviation in place of the population standard deviation. And of course, I said under this condition that, which means I have my solution. I said that under this condition, that what we have our this is this, we have that is x bar minus, we have what? Z of alpha over 2 multiplied by s all over root what? N, less than or equal to what? Mu, less than or equal to what? X bar plus what? Z of alpha over what? 2 multiplied by root, multiplied by what? By s all over square root of n, close it. From here to here is called your L, and from here to here is called your U. Remember, the lower confidence limit from here to here, the upper confidence limit from here to here. And then from this thing, I've already known what my X bar is, 2.2. I've already known what my S is, 0.3. I've already known what my N is, 49. The only thing I don't know is this my alpha. I don't know this alpha. Because I don't know the alpha, I'm going to use that same pattern I used before. What they want me to calculate now is 90% confidence level. And I already had told you, of course they are talking about percent, that this confidence level is normally given as 100 into 1 minus what? Alpha percent. Because you see where that alpha we are looking for is contained. So what you do is equate that confidence level given to you to that confidence level which you know that connects the alpha to enable you find the value of alpha. And this implies that you are going to have, this implies that you are going to have that 90% is now equals 100 into 1 minus alpha all in percent. So that this your percent and this your percent can go. And this will now give you that 90 is equals to 100 minus what? 100 what? Alpha. So that when this 100 comes over here, you have 90 minus 100 is equals to minus 100 what? Alpha. So that this is 90 minus this will give you minus what? 10 is equals to minus 100 alpha. Okay? So, and in that case now, what you're now going to have here becomes, this thing will cancel this one. So, and then, of course, you now have that your alpha now here, making alpha subject to formula all over 100. This is all over what? 100. So, this will cancel this. And alpha will not, therefore, my alpha is equal to 0.01. Because this 100 divided by this will give us a 0.01. Okay? So in that case now, when we now come over here now, we are now going to say, okay, fine, that what we now have here is what? If you say, yes, 10 divided by this will give us 0.01. Then we now go ahead. I've known everything I'm looking for. This is 0.01. So what I'm now going to do is anywhere I now see. So I'll now come here. I'll return back here. I've known the value of my x bar. It is given as 2. So I'll now come and say, therefore, this is going to be, my x bar is what? 2.2. So I have 2.2 here in place of x bar. The sign here is what? Minus. Let me go straight. This is z of alpha over 2. And I've known that my alpha is what? 0.01. So if you now divide 0.01 by 2, by this 2, you end up getting what? 0.005. Okay? So, and of course, we have been given that this 0.005 is given at this quantity, this value. Which means in place of this, I am going to use that value. So I'll say minus what? I have 2.575 for here, multiplied by, here is what my S, and my S is 0.13, 0.13 all over. My N is what? 49, so you take square root of what? 49. This is now for my U, okay? So for me to get my, which I will now say less than or equal to what? U, less than or equal to. For me now to get my U, it is going to be 2.2 plus what? 2.575 times what? 0.3 all over root of what? 49. Now close it. So obviously, once you have your calculator and you say 2.575 times 0.3 divided by square root of what? 9. Subtract whatever thing you get from 2.2. You get your L, which is your lower confidence limit. Come over here. This is 2.2 plus so it becomes 2.57 times 0.3 divided by this. Whatever value you get, you add it to this particular one, and then you have arrived at your answer. Okay? So that is exactly what we do in this one. So you are getting familiar to this, and most importantly, know how to arrive at the value of your alpha when you are given the confidence interval. That's what we do here. Thank you very much. Let us clean this and draw up another example. Our intention is to begin to take examples till it becomes a lot familiar with you, that you seeing a question is you understanding how to navigate your ways and be able to estimate confidence interval for that population of interests. Thanks for your audience thus far. Okay, let us look at this question together and see how we can solve it. That question says, and I read. So it is now going to be number 3. We are attempting number 3. Number 3 says, and I read, the mean weight of 16 packs of biscuits is 3.42 grams. The mean weight, which is x bar, of 16 packs. So my mean is 3.42 gram. My n is 16 packs. So I'll come here, I will see that my x bar is 3.42 grams. Then, of course, my n is equals what? 16. They mentioned it. And they went ahead and said, yes, the mean weight of 16 packs of biscuit is 3.4 grams. And a standard deviation of 0.68. So I have that my S is equal to 0.618 grams or 0.68. They say construct 99. Construct 99. Okay? construct 99 percent confidence interval. We should construct 99. This is 99% confidence interval for the population mean. That is C dot I for mu. For mu. Okay. So this it gave us a hint. They say hint that T of 0.005 of 15 equals 2.947. That's what they gave us. So what we are now going to do first of all is for us now to know exactly how we go about this particular one. Okay? So what we are going to do is we first of all check which category did it fall into. We now tell ourselves it fell into the third category. Here, my n is 16, so n is small. And then the population standard deviation is unknown. That's why they calculated it from this sample they took, and S is equals to this. And I told us that in that third condition, that what we have is that we open a bracket, that our x bar minus, we have, instead of having z, what we are now going to have is what? T of n minus 1 of alpha over 2 multiplied by, we have what? S all over root what? N. Less than or equal to what? Mu. Less than or equal to, we have what? X what bar plus T of n minus 1 of alpha over 2 multiplied by what? S all over square root of what? N. We close the brackets. So here, what you do is this. You know what your x bar is. You know everything here. You know what your x bar is to be this. You know what your n is to be 16. You know what your s is to be this. But you don't know alpha. You try and do what I've been doing before. So you just have this to be 9, 9. Okay? So you now have this is 99% equals, here is 100 into 1 minus what? Alpha of what? Percent. So that if you cancel this your percent and cancel this your percent, this thing will give you that 99 equals 100 minus what? 100 what? Alpha. This will give you 99 minus 100 equals minus 100 what? Alpha. This will give you what? 1 minus 1 is equals minus 100 alpha. And then this will give you, minus will cancel minus. This all over 100 is all over 100. So 100 will cancel 100. This is alpha. Think 1 divided by 100 will give us 0.001. I guess 0.001. You can confirm that thing to know whether it is true. 0.001. Okay? So in that case, meaning that the other one we solved earlier where we used the 90%, I think you need to press your calculator very much well to confirm whether that alpha level we got there, how correct that alpha level is. I'm doing these things without a punching calculator. Sorry if my joy is that you have really understood the process of doing it. So when you come here now, you now return back here. Anywhere you see your this, I know what my this thing is. So I will now come here. So I will now say that this thing is now going to be, here is my x bar, which is 3.47. I have 3.42. 3.42. The sign here is what? Minus. Here, remember that this my n minus 1 is what we call degrees of freedom. And my n here is what? Is 16. So 16 minus 1 is 15. So 15 is the degrees of freedom. 15. So what you are going to have here becomes what? Your t. Here is already your alpha. And your alpha has been gotten to what? 0.001. If you divide it now, you are going to have 0.005, I guess. Try and punch calculator and confirm these ones. I'm doing it without a calculator. So now you have this one to be what? So if you divide this, you have 0.005. So 0.005. Your n is 16. 16 minus 1 is 15. So you have here to be 15. Multiply by. Here is your s, and your s is what? 0. What? 6 what? 8. All over. Square root of what? 16. This is what? 16. Less than or equal to what? Mu. Less than or equal to. You now come for the upper one. It becomes 3.4 plus. The same value here, you have t 0.05005 15, then multiply by 0.68 all over root of 16, close the bracket. So the moment you pick up, of course, you know that this thing has been given to me as 2.947. This value, look at it here, T15 of 0.005, look at it. That is the student T distribution of 15 degrees of freedom with this level of significance has been given to me as this. So you just need to put up the value here and multiply out, and whatever you get becomes the value. So what I'm trying to drive at this is that when you are giving questions in this particular confidence interval on the population mean, let your interest be on whether the sample size is large and whether the population standard deviation is given. The moment they are given, you know what to use. The moment they are not given, you know what to use. When they are given, when the population standard deviation is known and the n is what is large, you use step 1. When it is large but the population standard deviation is unknown, you use the second one that makes use of s. But eventually, when the sample is size is what is small and then the standard deviation is what unknown, do not go and use z, use t in place of what? Of z. That's what I want you to drive at, to get at in this particular one. Thank you very much for your audience so far. Let me clean this and be fast to manage the size of this video. Okay, what if now our interest is to build confidence interval for the difference of two population means? This is different from a population mean. When we talk about population mean in the first place, we just had only one population. But this time around, we are saying that we have two populations, where this one has its own mean and which one has its own mean. And we want to develop a confidence interval of the difference between these two population what means. What do we mean by difference between two population means? Situation whereby you have population 1 and population 2. You have what we call population. So construction of a construction of confidence interval for the difference. Please permit me to write difference here. To write difference this way, or permit me to write a DFF dot. Difference between two population means. Two POP means. POP means. Okay? So in this case now you have population 1. You have population 1. Let me be writing POP 1. You have a POP what? 2. That is population what? 2. And then from this population 1, you are having what we call mu 1. And then in this population 2, you're having what we call mu 2. The difference between these two things now is what we're now going to say mu 1 minus what? Mu 2. So the confidence interval you want to build is a confidence interval that is going to contain mu 1 and mu 2. And we are still saying let it be that our L and U. Such that in this case now, what you are now going to have here becomes what? That our L is less than or equal to what? Mu 1 minus what? Mu 2. Which is less than or equal to what? U. Bringing in the issue of probability then, you are now going to see that you are having that P of what? L less than or equal to what? Mu 1 minus what? Mu what? 2. This is mu 1 minus mu 2 less than or equal to what? U is given as 1 minus alpha. Or you can still have it as what? P of L less than or equal to what? Mu 1 minus what? Mu what? 2 less than or equal to what? U, close the bracket, times 100% is 100 into 1 minus alpha percent. So our interest here is how do we obtain the true values of L and U, which is the lower class limit and the upper class limit that is going to bound or contain the difference between the two population means. Here is how are we going to obtain the true value of L and U that are going to contain the difference between the two population means uh, mu1, the difference between two population means mu1 minus mu2 with 1 minus alpha level of confidence. The same thing applies here with 100 minus 1 over alpha level of significance. We are equally going to do all these things now based on condition. Based on what? Condition. And we are going to specify those conditions on the board. Okay, so thank you. That's what we are doing for two population means. Let me quickly clean here. You have known what we are now doing. Our interest is now, how are we now going to obtain true value of L and U with this level of confidence? How do we obtain the true value of L and U with this level of confidence? That's exactly what we are doing here. You understand? So permit me to clean the board. So what if now they say that two random samples were taken from two different populations, where of course we know that we have population 1 and population 2. So in that case, the sample they are going to take will now be that they have x11, comma, x12, comma, up to what? x1, n1. N1 here is talking about that this is coming from population 1. This sample of n here is coming from population 1. And then we have what we call x21, comma, x what 22, comma, up to what x what 2, n what 2. This n2 here is talking about that it is coming from what? Population what 2. Okay? And then of course these samples here I have here now, of course, they are coming from two populations, population 1 and population 2. And those two, population 1 and population 2, are going to have what we call, population 1 is going to have what we call mu1 and sigma squared 1. And population 2 is going to have what? Mu what 2 and sigma squared what 2. These are what we call the mean of population 1, the variance of population 1, the mean of population 2, the variance of what? Of population what? 2. And then you have taken your sample, and from this your sample you are going to calculate your what? Your mean. Okay, so when you calculate your mean here now, what you are now going to have is that here you are going to have what we call x bar 1, and here you are going to have what? X bar what? 2. And we are now saying, how do we now construct a confidence interval for the difference between these two population mean, mu1 and mu2? That is the confidence interval of that my L is less than or equal to what? Mu1, less than or equal to mu1 minus what? Mu what? 2, less than or equal to what? U. How do I find the true value of L and what? U? That is what I'm doing here. What do I do in this case? We are now going to do it under conditions as well. Number one condition, number one, is when our sample size are large, and the population variances sigma 1 squared. So when n1 and n what 2 are large, and sigma 1 squared and sigma 2 squared are known. What are we now going to do when this condition is what? Is true? What we are now going to do now here is what is the value of my L? What is the value of my what? My U. The value of my L here in this case becomes that I have that my L is going to be x bar 1 minus x bar what? 2. Open a bracket and close it. Minus. You have what? Z of alpha over what? 2. Then square root of what we call a sigma square root 1 all over n1 plus sigma square root what 2 all over what n what 2. The sign here is what? Less than or equal to. Here is my what? My mu 1 minus what? Mu what 2. Then here is what? Less than or equal to. Everything here still remain the same except that here is going to be positive. So you open a bracket here, then you now have what we call x bar what 1 minus x bar what 2, you close it. Here becomes what? Plus z of alpha over what? 2 square root of what we call sigma 1 squared all over what? N1 plus sigma 2 squared all over what? N what 2. Close the brackets. So this is the formula you use in this case. Because in the question they will be giving you, or what we might be seeing, is where they have told you that the population variance of the first population, or the variance of the first population is sigma 2 squared, sigma 1 squared. That of population 2 is sigma 2 squared. Then have given the value of what? N1 and N2. So your own is just to sort. The only thing you'll be looking for here is your alpha. And then that alpha, they must have told you, construct a particular confidence interval. And from that particular confidence interval, you'll be able to know what is your value of your alpha. And the moment you know your value of your alpha, you divide it by what? 2. You go to standard normal distribution, assuming that the hint is not given. You go to the table of a standard normal distribution and read up the value of a z of a particular number there. So this is what you use when the N1 and N2 is what is large, and then this and this are what are known. Now, we have a scenario. Another scenario we have is now, what if now our N1 and our N2 are small, but sigma 1 squared, sigma 2 squared are unknown, but they are assumed to be equal.